Nice. So guys joining online, please make sure to mute your microphone. If you have a question, please send it in the chat and then I'll see that. Yep, thank you. Unless if I'm asking a question, then you guys can unmute and respond. You guys think we're waiting for the previous slide?
Normally it's a lot.
Okay, but it's getting emptier.
Yeah, I mean, the first week it was
Really?
Yeah.
Wow.
it's got smaller and smaller as the week.
Yeah, that's not good. That's not good. I think the hybrid system makes it easy to view it from anywhere. And has its own pros and cons. Pros, you know, you can review it, basically go through the lecture again, but the cons are really students tend to not to go to them. Yeah, it's just the traffic and stuff, which I don't think it's a good experience. I mean, you benefit from the in-person experience a lot differently than the online, but still, okay. We'll wait another minute or two. Wait another minute and then we'll start. Okay. Okay, awesome. Let's start. So let me. Hello everyone, nice to meet you guys. I'm Hussein Haidari and I'm a lecturer at the School of Engineering and Materials Science. I just joined last October. I did my PhD in Berkeley, California. My area of expertise is 3D printing, additive manufacturing. So if you're interested in those areas, do reach out to me and I can just navigate you in the right direction and find a project that you'll be interested in being part of. And then basically once I graduated, we had the startup company in Texas doing 3D printing for organ scale tissue manufacturing. So we were printing these large hydrogel constructs that could host cells at, you know, very high resolution and high speed. So I'll tell you a little bit more about that in the next couple of lectures, but today we're going to sort of review the quiz that we had. These quizzes, I encourage you to take them ahead of the lecture. Definitely do that, although it's not graded, because that's what we're going to discuss throughout the lecture. We're going to do the same next week and the week after as well. Last week, week 12, I may have a recording of this lecture for you, but we'll see how that goes because I'll be at the conference the next half of that week 12 session. But this is my email in case you've got the wrong email, which is the same .haydari. It's basically h.haydari@qmul.ac.uk. And please reach out to me if you have any interest in these areas or about the module remaining content. The content this week is focused around the geometry, the structure of these chemicals called polymers. And we're looking at how we synthesize them, how the properties vary. And we're just looking at chemistry for now. Next week, we're looking more at the mechanical properties and testing these and looking at their behavior under different conditions. There is one point about the quizzes, that is the grading scheme. You may have found a little bit confusing. We have positive, I'll get to that in a minute, but you have positive points for the correct answers that you make. But if you make an incorrect, if you select an incorrect choice, then you'll get negative points. And that's so that if someone just randomly selects all the choices, they don't get 100%. So that's all we can do. Before this, it was all or nothing in the previous year. But the problem with that was that even if you got part of the answer or found one correct choice, you didn't get anything. So it was a little bit unfair. So we sort of moved towards this approach, but it's still, each of these have their own pros and cons. Now, the last thing I want to mention before we get to the questions is feedback and evaluation. We personally haven't had a chance to meet that much, but please do evaluate the module based on what you enjoyed, what you felt was a pain point of the module and could be improved. Those really help us improve the module. If you don't know already how to find that, it should be in your email, but also the ARCS module evaluation page. If you can find that online and place your feedback there. So your voice matters a lot to us. Okay, that's the only way we can make the school and the programs and the modules better. Okay, finally, I'll try and point out some good resources if you're interested in polymers. This UL Prospect is one of the giants in polymers and plastics. They usually have webinars. If you're interested in plastics and polymers, there's lots of online resources, but these live webinars are a chance for you to go there, ask your questions from the speaker and get more into the details of the topic. Okay, let's jump into the questions because a good amount of detail to cover here. So the first question is asking you about the molecular weight distribution, and it's giving you the number fraction. So it's asking for the number average molecular weight. Okay, this is a typical thing to ask for when you work with polymers, and the reason is that one of the biggest challenges with polymers is the fact that the process of making them out of monomers is a very difficult process to control at the molecular level. So chain reactions initiate, propagate, and terminate randomly in time. We can't control temperature and everything else finely at the molecular level because diffusion, thermal conduction, all of that makes it very variable across the entire volume. So you end up getting various molecular lengths and weights for these polymeric chains. Now, we can't solve that problem fully, but at least we can explain the behavior and try and use that in selecting our polymer. And what we can do afterwards is if we're not happy with it, we can filter out the molecules that are smaller using a dialysis process where we have a membrane, we filter a certain molecular weight out of the mixture, and we're left with the remainder. Okay, so what you've got here is a certain type of distribution. Does anyone know what it's called? What sort of distribution? Normal distribution. And this is a Gaussian sort of bell curve. Peaks here and then falls down to the extremes. And this is sort of representative of the data that you see there. a very minimum content in the two extremes. And here in the middle, it's maximum number, sort of population density. Now, how do you approach this problem? Well, unlike the other problem that we had in the recording, where you had a single value representing each group and population, here you have a range. So you have to find a representative for that range. And what you do is you find the mid value, use that as a representative. So for that first one, we found mid value is 22,500. And we do that for all of those. And then we multiply that representative by that number fraction. And we basically sum those up in order to get the overall average. Now, you may ask, okay, so well, this is a statistical thing. What does it mean to have two types, weight and number based? Why are each of these important? Why don't we just use the number average? What's the, apart from the statistical significance, what is the physical meaning of that? So if we go back to, this line, you'll see that the number average fits right here where the peak is, and the weight average a little bit further down, leaning towards the heavier side. Now, the first thing, I'll get to that question in a minute, but the first thing that really matters is, why is the weight average leaning towards the heavier molecules? So those averages, one is based on weight, the other is based on the number of moles. Okay?
Yeah, well, because there are much more, like a larger number of molecules that are heavier than lighter.
Not necessarily. I mean, it could be a fully symmetrical one, and there's the same number of heavies and lights. Okay, but yeah.
Because like the molecules are different sizes, so and there's a set amount of quantity, but the weight different sizes and
Heavier.
Yeah.
Okay. Almost getting that. Yep.
Because like with these polymers, you've got a backbone of carbons and a series of hydrogens. There's always like usually like two more hydrogens for each carbon in a normal standard sort of polymer. So therefore, as you add more numbers of carbon hydrogen polymers onto it, your weight is going to actually go up by 3 molecules rather than 1.
So whenever you add a carbon, you add 2 hydrogens with it, because the terminal ends have the same 3 atoms, right? So actually, towards the smaller end of things, the variation is more significant as you go towards longer ones with adding to. So that doesn't affect it as much. But yeah, it's not the change of mass by adding carbons isn't uniform. But here we're not even talking about, so we're just talking about the statistical meaning of it. Why is the weight average greater than the number average? So the reason is, when you're taking the number average, a small molecule has 1 vote and a large molecule also has 1 vote. So whether it's a heavy molecule or a lightweight molecule, it's equal between them. They each get 1 vote because we're counting them. We're looking at the number of molecules. So it's very much what you just said. The heavier ones contribute more when you're looking at the weight average because they weigh more and they get a greater votes there. When you do number based, each molecule gets 1 vote. So it's very much equal. That's why it lands right here. When you're taking the weight average, okay, what happens is that you're looking at the weight of that subpopulation, right? So you're looking at the weight of this particular subpopulation over the overall weight. And because by nature they weigh more, they're the heavier molecules, they're going to have a greater say in the entire average. Okay? So that's why you have this. So these actually can be very much symmetric, but you'll see that the weight average and the number average do not align. Okay, is that clear to everyone? So for those of you who just arrived, I was asking, why is the weight average heavier? Why does it lean towards the heavier side? than the number average. And the reason is the number average judges and finds the average based on the number of molecules. So each molecule, whether it's small or large, gets the same vote. Each has a vote. But the weight average gives votes based on the weight. So the heavier ones play a more important role here. And so that's why they push it towards the heavier side. Yeah. Yeah, pretty much in any normal distribution, at least, you have this. Okay. But of course, weight isn't necessarily something that in statistics we find it important, because not everything is categorized based on weight. But yeah, if you have a normal distribution, it's always going to be that. And if weight is something meaningful in your case, interest. Yeah.
Sorry, I still don't understand, what does the number average like represent? For example, like if we want the average weight, we take the weight average. But what does the number average like represent?
Each of these are an average. So these do represent an average, but physically, is that what you're right? Yeah. So physically, these come into play when you're looking at a chemical reaction and putting this polymer in and getting the product out. Okay. When you zoom in at the molecular level, okay, the mass of that molecule is, in other words, the presence of it in that space. It's also the volume that it can see, right? The tiny ones are going to be isolated tiny molecules, very rare to reach because they're sparsely scattered in these larger molecules. So if you're looking at the probability of the reactions in U, then you care about their presence in terms of weight fraction. If you're just worried about how many molecules am I going to get, you care about how many moles of the small one you have, how many moles of the larger one. You don't care about the physical presence. That's why it's more at the molecular level, when you zoom in, that you actually notice that each of these, the researchers that are doing experiments, they mean something slightly different. Okay, so it's not just a statistical thing, it has some physical meaning to it, and you'll get more of this as you move forward. But the next part actually wants the flip side of this. So it's asking, what is the weight fraction for each of these categories? Yeah, go ahead.
I had a question on this.
Yes.
So, doesn't that mean that if you have a polymer, it's and the certain section is was comprised of short polymers, and certain sections comprised of long polymers. The short polymers being able to, let's say they both have the same volume. There'll be more short polymers in the specific polymers, large polymers. Doesn't that mean the number average could be different?
Yes. So what you're saying is that the weight percent is equal. So you have all the set. You have the same volume of the small ones than the same amount that you have in the large one. So you have more of the small ones, right? So that case, the number average, okay, the number average for the small ones will be greater. Okay, in other words, number average will lean towards the smaller ones. Okay, but it doesn't mean that the weight average is going to go behind the number average. Okay, this is always going to stand where the number average and the weight average position, so that the weighted average is going to be heavier. If your distribution is no longer normal, so it's like that, where the smaller molecules are taking the massive chunk, I said that doesn't hold, right? The fact that weight average is always greater than number average only holds if your distribution is normal, right? So, yeah. Okay, so that makes sense. So that's just something to give you an idea of, you know, a little bit more clarity as to what each of these averages mean, the individual meanings. So now the second question is asking you about the weight fraction. And you already have a bit of the calculation done. And this is the problem. If these cascade questions, if you fail to respond to one of them, or if you get the wrong answer, sorry, I think someone has their microphone. Let's see. Okay. So if you get one part of the question wrong, the other part will follow using that data. So I encourage you to spend enough time calculating the first bit, and that time will then pay off as you get to the next question. Okay, we're always going to have this case and B split, by the way. It's going to be at least 2 questions from this same table. Now here you've already calculated the number average. You're now trying to figure out the weight fraction. Okay, so how do we do that? We're going to find the weight associated with each subpopulation and divide it by the overall weight. So how do I proceed with this then? How do I find the overall weight?
We can take the middle point of each molecular weight range and multiply it by like the frequency.
Yeah, the number fraction. Yep.
Yeah.
And then divide it by that. So what are you doing? In essence, what you're doing is you're saying, okay, so let's say I've got 0.04. That means if I've got 100 molecules, 4 of those 100 molecules belong to that group. So what I'm going to do is, let's say for the 45 to 60K, right here. How many molecules out of 1,000 are in that range? 160, right? Because it's 0.16. So let's say my overall number of molecules was 1,000. I have 1,000 times the average, the number average, which is 73,800. So this is my overall weight. It's the number average times the overall number. Up there, I have the subpopulation number of 160, and that's going to be multiplied by the average here, which is 52,500. Okay, so what do I have here? I have the number of molecules in that subpopulation times the average for that subpopulation, the number of overall molecules times the average for the overall group. Now, the reason I did this was this actually goes down to what you just mentioned, which is 0.16. It doesn't matter if I have 1,000 molecules, 100,000. It's always going to be the ratio of these numbers, these two numbers, these two populations, going to be the number fraction for that group, right? So all I have to do is to multiply the number fraction by the representative weight for this subcategory, and then divide it by the overall average. Okay, so that's what you do in order to calculate the weight fraction. Now, it would be the worst torture would be if they asked you to now calculate the weight average molecular weight, right? So that way you'll have to find the weight fractions for each of these, and then find the product and sum based on those. Okay, that would take the most time. Okay, but to calculate it for an individual subcategory or subpopulation, it's pretty fast to do that. Okay, so if we do that, we'll see that we found the mid value, we've multiplied by the number fraction, and then we divided it by the overall average. Okay, so it wouldn't matter how many you have. This is just to explain that. And for the other group, it's going to be the same story, and you should get 0.11 and 0.12, those two values. Okay. Next question. So it's given you the structure for the monomer. Okay. So single unit. Is this actually the monomer? Yeah.
Remember the previous question, why do we
Oh, this one.
Yeah.
I gave you an example. I said, let's say there's 1,000 molecules. 160 of those are going to belong to this group, right? So I found the mass associated to this group by multiplying the number of those by their average, the number average, and then I multiplied the overall number of molecules times the overall average. This is to find the overall mass, and that's the subpopulation mass. Yeah, so in other words, I was trying to derive the fact that it doesn't matter how many out of how many you have, it's the proportion of those that actually counts to calculate. So yeah, all you need to do, yeah, just find the mid-value average for that subpopulation, multiply it by the number fraction, and then divide it by the overall number average. Yeah. So is this the monomer? Is this the monomer? it's what we call the repeating unit, right? It's missing the two H's on the two sides, okay? So it's basically the monomer, apart from it's inside the polymeric chain, so it's missing the two terminal hydrogen, okay? So we call it the repeating unit. That's why if we give you the monomer, you have to subtract the two H's. We don't use those in calculating the repeating unit mass, okay? If you find this, you just simply, you know how many of each atom you have, you simply add them. And you've got the mass associated with each repeating unit, okay? And all you have to do is now divide that average molecular weight by the weight of each repeating unit, okay? And what sort of DP is, this is degree of polymerization. So what sort of degree of polymerization is this? Is it weight average or number average? You're using the number average molecular weight, so you'll get a number average DP as well, right? So degree of polymerization, another very important thing. So molecular weight is a very important concept, and we want to know what the distribution is. But so is the degree of polymerization, meaning that how many of these tiny units do you have in the full size polymer chain? That tells you how long these chains are. And so here you can see that you can easily calculate that based on the overall mass of that chain. And this time we're looking at the average chain in this system, and that average is based on the number fractions, not the weight fractions. Okay, let's see if we have any online questions and all. Okay, so cool. So let's go back. So next question is asking you about crystallinity. Another important characteristic of polymers. We ideally want them to all be nice and crystalline, but that although that makes them stronger, it makes them also brittle. Okay, but as with any crystal material and form of matter. So the fact that they have amorphous regions is what makes them plastic formable. Okay, so it's very difficult also to get fully crystalline polymers. It requires a very carefully controlled single crystal growth mechanism as you do the polymerization reaction. But then apart from that, you have, in most of the cases, you have amorphous mixed with crystalline. And in this case, they've given you sort of a mixture of two different components. There's a composite material, and then they've polymerized everything to give you the final mesh. And they've given you the density of each. Now, before we start solving the problem, what I usually like to do at the beginning is look at the equation and try and understand it a little bit better. By first trying to pop in some values, some extreme values, to see if it's actually functioning the way it should. So let's say this semi-crystalline structure that we're talking about is actually fully amorphous. So this is unknown, but let's say I'm telling you the rho sub S, which is the density of this semi-crystalline, is actually equal to rho sub A. So the material is fully amorphous. If you substitute that there, what will that give you? Zero, right? So it actually works. It tells us the percent crystallinity is zero if it's fully amorphous. What if I put rho sub C, which is fully crystalline, in the equation? If I substitute it there, what do they give me? 100. Yes, because it's going to be then rho sub C. If I substitute there, minus rho sub A over rho sub C minus rho sub A, so I can cancel these. Now I've got rho sub C over rho sub C, also 1. So it's 1 or 100 if you multiply it by that. So that absolutely works to the two extremes. And if there's something in between, it's always going to give you something between 0 and 100. Okay. Now, in this case, all I have to do is to figure out what my density for the semi-crystalline state is. So I take the average for the two composite materials that I've been given. It's a 1-to-1. So I'm just going to find the average. And then all I have to do is to substitute that for rho sub S. And what it gives me is the overall percent crystallinity. Okay, so it's almost 50-50 amorphous and crystalline. Yeah. Yes. Yeah, then you just give it 2 votes. So when you're finding the average, if it's like 2 to 1, then you multiply that by 2, this by 1. It's again going to be a statistical thing. 2 times that, 1 times that divided by 3. So it's just very much an averaging, but it's averaging based on the volume ratio. Yep. Question 2, yes. Question 2 was 3 or 2. Yes. Yep, yep. Cool. So any questions about these questions 3 and 4? Yep.
I thought you did separately.
You
did separately.
In this question?
No.
Oh, okay. You talking about question number 4, the crystallinity?
Yeah.
Oh no, that'll give you. I think that'll give you a different answer because it's both present in the denominator and the. Yeah, I think that's going to be an issue. Yeah, you should find first of all the density belonging to that, and then use the extremes to calculate the percent crystallinity. Yeah, yeah.
It's the only reason why we're able to do to add the densities and divide it by 2 because the volume was 1 to 1.
Yeah, it was a 1-to-1 ratio, so you know the mixture density at the end of the mixing process is going to be a 1-to-1 ratio. Yeah.
I also had another question about this question.
Yeah. But
Why are we using the molecular weights? The midpoint of the molecular weight when it's against the number average to calculate our ratio. Sorry, times 0.16.
oh, so you're saying why is the representative for each subpopulation the mid value?
So why are we using the mid value divided by 73,800 times 0.16 to get?
That's why the reason I did this was to explain that. So I was saying, let's take a hypothetical case where we have 1,000 molecules, 1,000 chains inside this sample. Okay. So what's the overall weight going to be? It's going to be 1,000 times the number average. The number of molecules times the number average, right? And then for each subpopulation now, you can figure out how much that is. So that's going to be 160 times the number average for that, which is basically the average mid value. And now what this tells us is that this proportion is what matters. They're always going to cancel out to become the number fraction, basically. So regardless of how many chains you have there, it's always going to be this formula, because I realized when you put it like this, it's going to be confusing. So start with the sort of numerical example, and then you'll see how it all makes sense. Does that make sense?
Makes sense.
Okay. Yeah.
It's 73,800 number average on the weight.
It's the number average that we calculated a little bit ago. So because it was a number average, that's why I used it to find the overall weight. I multiplied it by the number. If it was a weight average, I should have multiplied it by still the number, but it would have been, yeah.
It's reversed.
Huh?
It's reversed. So we use.
Yeah, so exactly. Alternatively, I would find the overall weight divided by the number to get a number average. That's usually the way you do it. But here I'm using data that I already calculated to figure out what the overall weight is. Yeah, what's confusing about it?
I don't get why we're using number. Yeah, wait.
Oh, so if you could do it, I mean, using this data, you could do it in other ways too. For instance, you could just multiply all of these, right? And then find the overall. That would be the overall mass, right? But the question then is this. So you've got the overall average and you've got the subpopulation average. But then to convert it to that ratio, you're wondering how many of these do I have? Because you want to get the total. And the answer is it doesn't matter. The proportion of these two matters, not the individual. So in other words, yeah, you just need to divide this but multiply it by the number fraction. Let's talk, yeah.
So it's eventually showing us that it's showing us the weight of in that range.
Mhm.
The total weight in that range divided by the total weight of all the molecules.
Everything, yeah, so all the molecules, yeah. So you're getting the average for everything times the number for everything, the average for that subpopulation times the number representing that. That's why it works. You could have done it with other data that you had here. If it was another distribution through the weights, you would have done the same story. Okay. So now let's see what we've got here. So, oh yeah, we already. So this one's asking you about these isomers. That first two, 1 and 2, are they isomers?
Yeah.
Yeah, 1 and 2 are. So what do? We have to figure out, how do we figure out whether they're isomers or not?
Okay, which end of the line?
Exactly. We just count the number of atoms. And in this case, we've got the same number of carbons, the same number of hydrogens. We've got 1 oxygen. So those are isomers. What about 3 and 4? They're also isomers? Yeah. Okay. So clearly, second choice is correct, and choices 1 and 4 are not correct. Now, what about this last choice here? 1 and 2 are stereoisomers of pentane. Is this part correct? No. Because pentane, what's it missing? Oxygen. So there's 1 oxygen there that these have, but pentane doesn't have. Is pentane the smallest member of the polyethylene family?
It's ethane.
Which one is pentane? I'm saying, is this correct? Is it the smallest member? It's not, because members of this family have even numbers of carbon, right? 2, 4, 8. Actually, the smallest one has 4. Yep.
What do you mean, family?
Oh, that's just a group of polymers, okay? That are all polyethylene. So polyethylene could be 2 ethylenes, 3 ethylenes, 4 ethylenes. It's just chains that are built up from it. Yeah. So that's what they are. And this one does not belong to that family. Neither is that correct, nor is the first part correct. Okay. So that was clearly incorrect. But what about the third one? The third choice. So these are they? What does saturated mean? Is that the double bond turns to a single bond. And why do we say saturated? Exactly. It's using its maximum capacity to link and bond with other molecules. So when it's a double bond, it's not using that maximum capacity. It can open up and connect with 2 more hydrogens, each atom can. So that's why if you saturate that, what's going to happen is that it will become butane. And is it the smallest member of that family? Yeah. Yeah, why?
It's 2 and 2 and things too, so.
Yeah. Okay, so it's, the thing is, some say that, the molecule itself, ethylene or ethylene, is actually also part of that family. But the broader accepted reality is that this is a poly. It has to be at least 2, right? More than 1, exactly. So you're absolutely correct that it's 2 or more. The smallest member is indeed 2. So it's 2 C2, which gives you that C4. Yeah. Okay. Does that make sense? So both of those are correct statements, and that's why this one is correct. Okay. Any questions about this one? Yeah. No. Okay. What about what? Yeah.
Stereoisomers.
These. Okay. So first of all, are these stereoisomers? The first 2. No. What about the second two?
Geometric.
Geometric, are they? Cis or trans? Huh?
Number second stereo.
Huh?
It's geometric, same as stereo.
So, so let's look at that. Actually, I have the slide for that one here. Okay, so first things first, not every two isomers belong to this categorization. These are special categories that isomers can belong to. Okay, so they can be geometrical isomers, meaning they're cis or trans. Okay, but they could be neither of those. And similarly, they could also belong to one of these groups, but they could also belong to none of them. Okay, so in this case, stereo, we're talking about the side groups. Okay, so how these are located. And if these are all H's, pretty much going to be stereo. Do we talk about the double bond here? Stereo?
You talk about the geometry.
Huh?
You talk about the geometry.
Yes, so here when we're talking about stereoisomers, it's fine. Those are stereoisomers if it's just the bond. So here, right now, we're looking at this structure. Did either of those first and second ones belong to this group? Sorry. So stereoisomers, they're very special. So it's either that you've got all the side groups on one end, or you've got them alternating with a certain frequency, or you've got them randomly there. So it's all about the R side groups, okay? Then you've got the geometrical isomers that are very much different to this, where the side groups, if you've got the backbone, okay, the side groups can all be on the same side. It's a cis, yeah.
I'm not going to let a double one say.
Huh? I didn't say there was a.
On the video, you're like, oh, come up with double one.
Which one? You talk about this one?
Yeah, both for the double ones.
Oh, this, because it's got, oh yeah, no, this is absolutely correct. It's got 4 bonds. There's no problem. Did I say it was supposed to be single?
Yeah.
Yeah, no, this is fine because it's got 2 bonds there and 2 on that side. I think you were the one who posted about the question. Yeah, but someone mentioned that. Yeah, I don't know why I said that, but this has 4 bonds, so it's absolutely fine to have that. Yeah, but do you understand that this is a little bit tricky to understand in a 2D drawing of the molecular structure, and these are very simple sort of subgroups of the entire chain, and it rarely happens that you have these 2 configurations. But if we go back to the question, what I was asking was, do these happen to belong to a certain categorization, 1 and 2? No, they don't, because it's got that OH group, which is randomly on one of the molecules that's the atoms of the chain. And in the other case, it's all the way to the end. So in terms of stereoisomers, they only have 1 group. We can't really tell whether the frequency is there or not, because it's just 1 group there. It doesn't belong to any of those groups. But what about geometrical isomers? Are those 2 geometrical? And 1 and 2.
There's no double one, so you can't compare.
For 1 and 2.
Yeah.
Exactly. They don't have a double bond, so the orientation only comes into play when you have a double bond. Okay. If you have a single bond, the reason double bonds do that is the repelling force from the electron in the bond that orients those in a certain configuration and keeps them that way. in this case, even if we had the double bond, you wouldn't have spotted that that geometrical isomerism based on what you have there. Okay, and 3 and 4 also don't have anything to do with those special cases. So none of these are geometrical isomers, and none of these are stereoisomers, meaning they have the special sort of frequency of features, side groups. So yeah, that's that. So any questions about these? Yeah.
Like reading what like these, I'm used to seeing them either in like the diagram at the bottom or just like ways into pentane and C5H12.
Yeah.
And not like the chain of CH3 and CH2. So I'm just struggling with the visualize it.
Exactly. So that's, yeah, this is one way of displaying these, is that you have the CH2s which are in the middle and CH3s which are the terminal ends. And so if you were to draw that, it would, I mean, again, depend on the bond structure. Not a chemist in any way, but so you have two H's there, and let's say you have a CH3, okay, it's usually, I mean, the 3D is going to be different now. What you have in this case is you have an OH group. Okay, so at the end of this, you have an OH group. So the situation is, again, with single bonds, this can rotate easily. That's why it doesn't mean a lot. That's why your classmate mentioned that you don't actually have that concept of cis and trans, because it doesn't enforce anything. So it's the conformality can change, okay, can rotate. But if you've got a strong double bond, then depending on the force field in that molecule, it can dictate which orientation it has. And it also depends on the previous and the ones that come after that single unit and how they actually interact with it. But it's not a question that I will ask, because it really depends on the molecular structure, and that is determined by the force field. It's difficult for you guys to tell just based on that. I didn't ask about that, and that's the reason here. But in general, the fact that we brought it up is just for you guys to know what stereoisomers mean, right? It's all about side groups, and when it's an H there, this concept doesn't even mean anything. We don't have any side groups here. Okay. Huh?
Welcome back.
Oh, the responses
No, the whole PowerPoint for this session.
for this session. Oh, I can upload this one. Yes. Yeah, I'll upload this. Yeah.
I thought stereoisomers were like when a carbon had 4 different groups in it, and it was like the superimposability.
When a carbon has what four?
So it had like 4 different groups, you know, like right and the left.
So a single carbon, or you mean like a polymer?
Yes, like a single carbon has like 4 different functional groups on it.
Yeah, so it has to have, at least 2 functional groups on it to enforce that condition. I don't know. I don't think you need 4 because.
Oh, yeah, my bad.
Yeah. But yeah, you need to have those functional groups. Otherwise, this doesn't even make any sense.
I just got mixed up, sorry.
Yeah, no. Yeah.
So whenever you look at that, sometimes you get bits of information that don't really cover.
Okay.
What how do I know this? For example, how cis component together uses rubber, natural rubber.
No.
Will you be testing?
Oh, so don't worry. If I give you 2 examples of materials, I'm talking about cis and trans. I just want to tell you the properties can be vastly different just because of that change in the chemical. I don't expect you to get a material, say, from a table and tell me whether it's cis or trans or whether it has a specific. I just want to tell you that it actually results in severe changes in the mechanical properties, for instance. Okay. This is an introduction to polymers. It's not an in-depth class. We've got the macromolecular engineering, which gets you into more details in a separate module. But this is really the depth that we're going to go into is to just sort of give you the overall vision as to what to look for when you're considering a certain problem. Okay, if you want to select a material, for instance, this won't fully explain to you just looking at the chemical structure what properties to expect, but you can sort of find some dots that you can connect between these. To fully understand that, it's the most beautiful thing is that you look at the chemical structure and you can quickly interpret from that this is probably going to cause this certain behavioral trait. Okay, but that's not what we expect this model. So if I bring these up as examples and don't really go into thorough explanation, that's because it's just giving you an idea that this can do this sort of influence. So yeah. Okay. Any question? Okay, wonderful. So again, this the last quick thing. So this sort of question has two right choices. Okay, so each choice is going to be +1 out of 2, and then it has 3 incorrect choices. If you mark any of those, it's going to be -0.66 because 2 divided by 3. So that's why if you select 1 correct choice and one wrong choice, it's not going to be 0. It's going to be +1 minus 0.66. So it's going to be 0.33. Okay. If it rarely happens that we have more correct choices than incorrect, then even if you choose 1 correct and 1 incorrect, you're still going to be negative. But it's usually, you get a positive point out of this. But please don't mark a choice that you're not sure about, because it just sort of neutralizes the positive ones. So, yeah.
Is the lower limit 0, or can we get like -1 for question?
Yeah, if there are more correct choices than incorrect, we'll get negative, but that won't happen. They use that to analyze the questions, but yeah, you won't get a negative. So we design it so that you have more correct choices, more incorrect choices. Correct. Yeah. But don't necessarily use that in responding. There could be a case that we've sort of made the software sort of give you a bias to make it positive. But yeah, no, you won't get negative. Okay, that's good. Okay, cool. Thank you. So online question. So the question 2, it doesn't mean that the number average is the same as the weight average. Those two are very much different. And as I mentioned, it's usually the weight average is heavier than the number average. I don't know why you
get that.
thought that. Yeah.
In the question say statements, how many just is like 2 or 3?
It depends on how many correct choices there are. There could be more than one. Yeah, exactly. Yeah, it could be any number. Yeah. Unless
I
they.
think it was only maximum 2, like that's like.
No, it can have more. Yeah, absolutely. It can have more incorrect or correct choices. Yeah, sure. Well, to find the weight fraction. Oh, so that was what we had. So the number average was what we had, and the equation that I used was I multiplied the overall number average by the overall number of molecules. Okay, so let's say there's 1,000 of these molecules in that sample. So you multiply that number average by 1,000, and then you divide that subpopulation's weight by that, meaning that out of that 1,000, you've got 160 times the average for that group. Okay, so that the idea was I was trying to tell you that the 160 and 1,000 always will cancel out to become 0.16. So it doesn't matter how many you have. Now, in this case, I had the numbers, so that's why I used number average. If you had a weight average, you would also do the same, but you've got to make sure that both the denominator and they both have the same weight average or number average used. And then in that case, instead of the number fraction, you would use the weight fraction. Does that make sense? And there's another question. For the last question, is there not a member of the polyethylene family that is smaller than butane? Yes, the butane. In that case, I think you're talking about this question here. Butane is C4H10, C2H6. Okay, C2H6 is just ethylene. So the problem with that is that it is smaller, but it's not a member of the polyethylene family because it's not poly. It's just a single ethylene. Does that make sense? So polyethylene family, we're talking about more than one repeating unit. So that's why the smallest member is 2 of those units, and that is the C4H10. Any questions here? Yeah. Yeah.
The concept of the stereoisomers confused me a bit because back at A levels under geometric isomers, we have stereoisomers, which were cis and trans, and then we have optical isomers, which was optical isomers. But now we have the one where we have the alternating, the random, and the stereoisomer.
Yeah, that so stereoisomers, unlike the geometrical means that you're comparing 2 isomers. You're trying to see, are they geometrical isomers to each other or not?
Yeah.
The stereoisomer, you're not comparing 2 things. You're just looking at one material, one polymer, right? If it has those features, sort of the side groups, positioned at that frequency, that sort of repeating directionality, and the other one has it in a different configuration, right? Those can be stereoisomers. So it's not so geometrical. You're talking about one of them has a geometry, the other one has that geometry with a tweak. Okay, so this tweak can be rotating it about that axis, okay, in a permanent way, not conformal, or it could be, you know, having it all on one side. But stereo is a completely different thing. It's all about the side groups, and it has to have, it's very difficult for it to have those 3 types, which is either they're all on one side, they're repeating on that style, or they're actually randomly there. But yeah, which part of it is it that
I now have more of that question. Do we ever see optical isomers in polymers?
yes, why not?
Okay, and so where do optical isomers classify under the whole scheme of things? Is they under stereo or geometric?
It would be geometric.
Okay.
Yeah, but stereo is completely different. Yeah, from geometric. It's whether or not the side groups are there or not. It's not just the you know, configuration.
Okay.
Yeah, but yeah, we can talk about this more in next lecture. So look at it from this perspective, and then I'll bring a few slides and talk about this, because I think, yeah, I haven't had anyone else asking about this specifically, but it's an important thing, so we'll talk about it a little bit more.
Thank you.
Sure, you're welcome. Any other questions? All good?
No.
Okay, take care. You guys do take. Okay, sorry. So here, 50 is the number average. Why do we divide the average 8 by? Oh, so let me see. Can you guys see my camera right now? Okay. You see the camera? So hopefully we've got another class here. So I have to end this. Sorry. This time it got super long, but thank you very much for waiting. Thank you. Thank you. Okay, so back to what you were saying. So what we do is we divide the weight for that population, that subpopulation. That's fine. I just turned it off because I don't have the whiteboard anymore. So we divide the weight of that subpopulation by the overall weight. Now, what is the overall weight? It's the number average times the overall number of molecules. Okay, so you've got the number average, you multiply by the overall number of molecules, but what is the overall number of molecules? We don't know. Let's say hypothetically it's 1,000 molecules. So you multiply 73,800 by 1,000. Now, what do you divide by this? So then you want to divide the subpopulation overall weight by this amount. So what's that weight? It's going to be the average weight of that subpopulation. Let me go to the side. So it's going to be the average weight of that subpopulation, which is 8,400, times the number of molecules in this subpopulation. That will give you the overall weight of this subpopulation. So if it was 1,000 in down there, here it would be 160, right? So you'd have 160 times 8,000 something divided by 1,000 times 73,800. Now you can cancel the 160 over 1,000 to make it 0.16. So it doesn't matter really if it was 1,000 or 10,000. The fraction would cancel out to 0.16, and you would only need to multiply that by the overall average and divide it by, multiply that by the subpopulation average and divide it by the overall. So that's how you get that. Does it make sense?
Sorry. So I understand what you did by 52,500 times 0.16. I get that part. You know, just the yellow part, 8,400 divided by 73,800. Because if we're finding the weight fraction, and 73,800 was the number average, shouldn't because you know the formula.
So we're not dividing it. So we are multiplying the 52,500 by 0.16 and then dividing it by that.
Yeah. So why do you divide it by 70,800?
So what is your overall weight? Aren't you supposed to divide the subpopulation weight by the overall weight?
So you know, okay, but isn't 73,800 the number average?
It is the number average, but you can go from the number average to the overall weight just by simply multiplying it by the number.
Oh, so if you multiply 73,800 by
the overall number, you will get the overall weight. Does that make sense?
But you divided it there. But you divided it. You didn't multiply.
So do this on a piece of paper. So your number average is 73,800.
Yeah.
Okay. And then assume that the overall number is 1,000. So you have 1,000 molecules. Okay. And then what do you put up there in this division?
So it's 1,000 times 70,800.
So down there you have 1,000 times 73,800, and you divide something by this. That's the weight of the subpopulation that you want to divide by this, right? So how much is that weight? It's going to be the average for that subpopulation times the number of molecules in that subpopulation, right? Now, what's the average? It's going to be 52,500.
Yeah.
But how many belong to this subpopulation?
8,400.
No, the number that belong to this, if you had 1,000 molecules overall.
Yeah. And
so
you multiply by 0.16.
Yes, so it's going to be 160 out of that 1,000, right?
Yeah.
So up there you have 160 molecules times their average, which is 52,500, divided by 1,000 molecules times.
Oh, I get it. Okay, but that 1,000, but that 1,000 cancel out essentially. So
and that 1,000 and 160 cancel out to give you 0.16, and that means that regardless of how many you have, that always the formula is going to be that proportion, which is 0.16 times the average for that category divided by the overall average.
Yeah. Okay, that makes sense.
Does that make sense?
Because they cancel out
yes.
essentially. Right.
Yes, that's what's going on. Yeah, I know it's a little bit confusing when you just look at the division there. So that's why I explained it based on a numerical example, okay? Whether you have 16 out of 100, 160 out of 1,000, whatever you have, it's the proportion of those that matters.
Okay, yeah, thank you so much, sir. Thank you.
Okay, sure, you're very welcome. Okay,
Have a
take
nice
care.
day.
You too. Have a good weekend. Bye.
You too. Thank you.